This video is on continuity. So the definition of a continuous function is that a function f is continuous at the value x equal to c if the limit as x approaches c of f of x is equal to f of c, the function value at that point. So the limit of the function as x approaches c must exist and be a finite real number and be equal to the function value at that point. So this implies that because the value exists and is equal to the function value at the point, f of c must be finite. Okay, let's look at the graph below. So this graph is discontinuous at several points. It's discontinuous at the point x equals -2 because the limit as x approaches -2 of f of x does not exist. So since the limit doesn't exist at that point, the function cannot be continuous by definition of continuity. It's also discontinuous at x equals 1.3. So it's discontinuous at x equals 1.3 because the limit of the function does exist. Limit as x approaches 1.3 of f of x does exist, and it's equal to whatever the output is, like 2.2 or something, 2.2. But it is not equal to the function value at the point. So that's not equal to f of 1.3 because f of 1.3 is undefined, at least as far as we can see from this picture. There's an open circle at f of 1.3. We also see that the limit as x approaches 2 of f of x does not exist because as x approaches 2, from the left we see that the function is heading towards positive infinity. From the right, the function is headed towards negative infinity. So there's no one single limit. That limit does not exist, and therefore the function is discontinuous at x equals 2. And finally, we see that at x equals 8, the limit as x approaches 8 of f of x does exist. It's equal to the output there. Looks like it's about +2, but that is not equal to the function value at that point. F of 8 is equal to whatever that value is. Maybe it's 3.5. So because the limit of the function is not equal to the value of the function at that point, f is discontinuous at x equal to 8. So we saw a couple different types of discontinuity above. So here are our types that we'll run into the most often. So if the limit as x approaches c from the left is not equal to the limit as x approaches c from the right, then f has a jump discontinuity at x equals c. If the limit as x approaches c of f of x is equal to a value L, but that is not equal to the function value at the point, then f is said to have a removable discontinuity or a point discontinuity at x equals c. And finally, if the limit as x approaches c of f of x is equal to positive or negative infinity, or the limit as x approaches c from the left is positive or negative infinity, or from the right is positive or negative infinity, then we say that f of x has an infinite discontinuity at c. And let's just check out our example. We see that at x equals -2, that's a jump discontinuity because we have different values for the left and right hand limits as x approaches -2. For x equals 1.3, that is a removable discontinuity, and it's a removable discontinuity because the limit as x approaches 1.3 of f of x does exist. It's just not equal to the function value at that point. We see that as the limit for x approaching 2 is an infinite limit situation. So at x equals 2, we have an infinite discontinuity. And finally, we see that at x equal to 8, we have, again, another removable or point discontinuity. So another removable or point discontinuity, because again, the limit does exist, it's just not equal to the function value at that point. So it could be, as in the situation at x equals 1.3, where the function is just not defined at that point, or it could be similar to the situation where x equals 8, where the function is defined at that point, but it's just not equal to the value that the limit of the function approaches. Another way to describe continuity that you may have encountered before is that a function is continuous if you can draw it without lifting your pencil. So that's an informal way of describing it, but we see it makes sense. We see that if we were drawing a sketch of the function above, we would have to lift our pencil at x equals -2. We'd have to lift our pencil to make that open circle at x equals 1.3. We'd have to lift our pencil to draw that positive and negative infinity that the function is going towards, and we'd have to lift our pencil when we got to x equals 8 to draw that open circle and the other function value at x equals 8. Some functions are continuous over their entire domains. That's all of their input values. So remember that domain is all input values that return a actual value for the function. So we can think back to functions and when limits are equal to the function value. So for example, polynomials, we know the limit is defined for any input value of a polynomial. Polynomials, therefore, are continuous for all real numbers, because for any polynomial, that's something of the form c1 plus c0 plus c1 x to the 1 plus c2 x to the 2 plus c3 x to the 3 plus ... So something with only integer or non-negative integer exponents for the variable and constants out front of it. Those are polynomials. We know that for any polynomial p of x, the limit as x approaches c of the polynomial p of x is just equal to the function value at that point, p of c, and therefore polynomials are continuous for all real numbers because the limit for any real number that you input is just equal to the function value at that point. Similarly, rational functions, remember that a rational function r of x is a polynomial divided by a polynomial. Those are continuous for all values of x such that the denominator is not equal to 0. So this is continuous when q of x is not equal to 0. And we know that when the denominator is equal to 0, we do have some situations where there's just a point discontinuity. So previously when we were using algebra to find limits of functions like this, if it was the case that the limit was equal, that the sort of problem canceled out on the top and the bottom for when the limit approached a value where q of x was equal to 0, then we've just got a point discontinuity, whereas there might be other situations where we've actually got infinite discontinuities. We'll see some examples in a moment. And finally, think back to a few videos ago where we looked at special limits. So if c is a real number in the domain of a given function, then the following limits hold. Observe this is just the definition of continuity, that the limit as x approaches c of the function is equal to the function value at c. That's the definition of continuity. So all of these are continuous over their domains. So these are all continuous over their domains because the limits exist and are equal to the function value at that point over their domains. And remember that the domains are just all possible input values that give a real number result. Finally, the sums, differences, multiples, powers of continuous functions are continuous. So if you've got two different functions that are continuous over all real numbers, then if you multiply those functions together, it's still continuous over all real numbers and so on. So let's use all these ideas to do a few examples. Let's determine the values over which the following functions are continuous. So we are figuring out what input values can we put into these functions that will have those functions continuous over those values. So we've got three different functions here to take a look at. F of x equals 4x to the 7th minus 2x cubed plus x sine x minus cosine cubed of x plus e to the x. That's our first function. Our second function is g of x equals x squared minus 1 divided by x to the 4th plus 4x plus 3. And our last function, h of t, is t minus 1 over t squared plus 5. So think about each of those and figure out for what values are those functions continuous. So it could be, for all x except certain values. It could be for all real numbers and so on. So pause and try those out. Okay, so let's look at our first function. That one looks kind of kind of confusing. There's a lot going on, but observe that the first part is just a polynomial. The second part is, a small polynomial multiplied by sine of x, which we know is continuous for all real numbers. So we know that sine of x is just that wave function that's continuous for all real numbers. The function value of sine of x is equal to the limit for any input value we chose. Cosine cubed of x, so remember that this is the same thing as cosine of x cubed. So this is just a special way that we denote powers of trig functions. And we know again that cosine of x is continuous over its domain. It's just the same kind of wave function but shifted over a unit of pi over 2. And so if we cube it, that's still continuous as well. And e to the x was also, if we look back at our special functions and those for which the limit always exists, this is also continuous for all real numbers. So each component of that function is continuous for all real numbers, and we don't have any situations where we could be dividing by 0 or doing something funny. So f of x is continuous for all real numbers. So we could write for all real numbers, or we could write over the interval from negative infinity up to positive infinity. Okay, so our next function is g of x, and we know that this is a polynomial divided by a polynomial. So the only thing we have to figure out is when is the denominator equal to 0. So those are places where the function is going to be discontinuous, but that's going to be continuous everywhere else. So to determine that, we could try to factor that denominator. So we want to factor x squared plus 4x plus 3 to determine when it's equal to 0. So x times x, and then we've got 3 and 1 as our last terms, and plus plus. Yes, that factors correctly. This is equal to our denominator. The x's multiplied to get x squared. The x times 1 plus 3x multiplied to give us 4x, and 3 times 1 gives us 3. So great, that's our factored denominator. And we see that that's equal to 0 if and only if either the first term or the second term is equal to 0. So x plus 3 equals 0, or x plus 1 equals 0. And that's if and only if x is equal to negative 3 or x equals negative 1. So those are situations where the denominator is equal to 0, and so those are situations where the function is discontinuous. So we could write our solution in different ways. One thing we could write is that we could say it's continuous everywhere else for x not equal to negative 3, x not equal to negative 1. That's one option. Another is we could say that it's continuous over a union of intervals, negative infinity up to negative 3, union the interval from negative 3 up to negative 1, unioned with the interval from negative 1 up to infinity. So those are two different ways that we could describe when g of x is continuous. Lastly, we've got h of t equals t minus 1 over t squared plus 5. So again, we'd want to look at, for this rational function, where is t squared plus 5 equal to 0? And our answer is nowhere, because t squared is greater than 0, or greater than or equal to 0, because t squared is always non-negative, and therefore t squared plus 5 is always greater than or equal to 5. So the denominator is never equal to 0, and therefore h of t is continuous for all real numbers, or we could also write for negative infinity to positive infinity. Now let's talk about continuity on closed intervals. So let f of x be defined over the closed interval from a to b, then f of x is continuous over that closed interval if two things are true. First of all, f of x must be continuous on the open part of the interval from a to b, and secondly, the limit as x approaches a from the right of f of x must be equal to f of a, and the limit as x approaches b from the left of f of x must be equal to f of b. Functions can also be continuous on half open intervals, like from a closed to b open, or a open to b closed. Let's just look at a quick example to make this make more sense. Let's think about the function f of x equals square root of x. So when we think about that function, we're just thinking about the positive half of it. If we think about it as a function, we're just thinking about f of x equals square root of x, which looks like that, half of a parabola turned on its side. We don't think about the lower half if we're thinking of this as a function, the negative square root of x, because a function must pass the vertical line test. The output of any value must have, for any input, there must be exactly one output for a function to be defined to pass the vertical line test. So f of x equals square root of x, we're only thinking about the positive square root of x. Okay, so where is this function continuous? Well, we know that f of x equals square root of x is just undefined for x less than 0. So the only place where it could be continuous is over its domain for x greater than or equal to 0. So let's consider the half open interval from 0 up to positive infinity. That's a half open interval where it's closed at 0, open at infinity, because we never actually reach infinity. We could also write that as 0 less than or equal to x less than infinity. Now let's think about what's happening for f of x over that half open interval. Well, we just looked at continuity over closed intervals. So here we're just thinking about the left-hand part being closed. And we see that, this is going to be, the first part of this is satisfied, that the square root of x is continuous over the open interval from a to b. So thinking about part 1, we see that f of x equals square root x is continuous over the interval from 0 to infinity, 0 open, because at any of these points the limit of the function exists. The function is continuous because we don't have to lift our pencil. The only possible issue we could have is at x equals 0. So for part 2 of what we need to verify, we only need to verify this first half in this case, because we're only thinking about the first half of the closed interval, the left endpoint. And we see that the limit as x approaches 0 from the right-hand side, of square root of x is equal to 0. So as this function approaches 0 from the right-hand side, the output of the function is getting close to 0. And so that's also equal to square root of 0, the function value at that point. And so that means that part 2 is satisfied as well. And so that tells us that f of x equals square root x is continuous over the half open interval 0 to infinity. All right, let's finish by doing some examples. Determine over which values the following functions are continuous. We already did number 1 actually. So think about those other ones. Pause the video and try those out, and we'll talk about them in a moment. Okay, so we already did square root of x. We saw that f of x equals square root of x is continuous over its domain. It's continuous from 0 up through infinity. And so that is where f of x equals square root of x is continuous. We could also write for 0 less than or equal to x, which is less than infinity. For the next one, we've got g of x equals the square root of 3 minus x. So this is going to be a really similar function, but let's just see what it's doing. So if we put in a value like, if we put in any value x greater than 3, then we see that g of x is going to be undefined. Because if x is greater than 3, like say x equals 4, then g of 4 would be square root of 3 minus 4. Square root of negative 1 is undefined, does not exist. So g of 3 is okay. 1, 2, 3. G of 3 has an output of 0. What about, for example, g of 2? G of 2 is the square root of 3 minus 2. That's 1. And so g of 2 would have an output of 1. And I think we can kind of see where this is going. So, for example, g of, let's see, g of negative 1, for example, would be the square root of 3 minus a negative 1. That's the square root of 4, which is 2. So g of negative 1 is an output of 2, and so on. And so we have that sort of sideways parabola. So it looks just like square root of x function, except it's flipped backwards and starts at x equals 3 instead of x equals 0. So this is the function of g of x equals square root of 3 minus x. And what do we see? That we see that this is continuous on the interval from negative infinity up to positive 3, because we could draw all of this without lifting our pencil. And then, so that means it's continuous from negative infinity up to 3 open interval. And because the limit of the function as x approaches 3 is actually equal to the function value at that point, because the limit as x approaches 3 from the left-hand side of g of x is equal to g of 3, which is 0. That tells us that it is continuous right up to that closed endpoint. So this function is continuous on the interval from negative infinity up to 3 closed. Now looking at h of x is the cube root of x. So cube root of x, h of x is defined for all values of x, so for all real numbers. Cube root of negative 8, for example, is negative 2 because negative 2 times negative 2 times negative 2 is negative 8. So cube root is defined for negative numbers, for 0, and for positive numbers. And the cube root function looks kind of like this. So cube root of 0 is 0. Cube root of, for example, as we said, negative 8 is an output of negative 2. And cube root of positive 8 would also be an output of positive 2. So that's the cube root function. And we can see that that function, it's defined for all real numbers, and it's continuous over its entire domain. So negative infinity to positive infinity would be our solution, or all real numbers. H of x is continuous for all real numbers. Now, t of x equals absolute value of x. So we talked about the absolute value function a little bit before. The absolute value of a function can be thought of as positive x for x greater than or equal to 0, and the opposite of x for x less than 0. Again, because if we put in a value like absolute value of 10, that's just 10, whereas if we put in a value like absolute value of negative 10, that's the opposite of negative 10, which is also positive 10. So that's the absolute value function, and it looks kind of like a V. So looks like that. Looks like just plain old x for x greater than or equal to 0, and looks like opposite of x for x less than 0, or the function y equals negative x for x less than 0. And so this is the function absolute value of x. And we see that for all values, for any input value, the limit would exist and be equal to the function value at that point. We can draw that function without lifting our pencil. And so again, this is over all real numbers, negative infinity up to positive infinity is our solution. For y equals tangent x, remember that tangent x is sine of x over cosine of x, and so we can think about when the denominator is equal to 0. So when is cosine of x equal to 0? We know that cosine starts at cosine of 0 is 1, and then oscillates, and that cosine of x is 0 for odd multiples of pi over 2. So those are points at which the denominator is going to be 0. And so tangent of x, we've sort of graphed it before and seen what it looks like. It's got asymptotes at all odd multiples of pi over 2. And so that's what, there are asymptotes, and tangent of x, as we've graphed before, looks kind of like that, and so on. Okay, and so that tells us that we've got these infinite discontinuities at all odd multiples of pi. So we could say that y equals tan x is discontinuous at x equals k pi over 2 for all odd integers k is one way that we could describe that. And our last example is y equals natural log of x. So remember that natural log of x is the inverse of e to the x, and natural log of x is equal to y if and only if e to the y is equal to x. So let's just first think about the graph of the function e to the x, because I think that's sort of easier to think about. E to the 1 is just e, which is like 2.718, so somewhere around there. E to the 2 is 2.718 squared, so something around 8-ish, and so on. We're getting larger and larger. It's an exponential function. E to the 0 is 1. E to the negative 1 is 1 over e, so it's going to be a small number. E to the negative 2, 1 over e squared, even smaller. And so we've got this exponential function, e to the x. If we think about what natural log of x looks like, then we've got the inverse. So one way to think about natural log of x equals y is just to reverse the x and y values. So because e to the 0 is equal to 1, that means that natural log of 1 is equal to 0. So that was e to the 0 equals 1 means natural log of 1 is equal to 0. Similarly, e to the 1 equals e means natural log of e is equal to 1. So if we go to 2.718, our output will be positive 1. And e to the negative 1 equals 1 over e means natural log of 1 over e is equal to negative 1. So if we look at 1 over e, a small number, we'll have negative 1 as our output. And basically, our function will end up looking like a curve like this. Another way to think about that function is that it is just reflected across the line y equals x. So it's the graph of e to the x reflected across the line y equals x. So that's natural log of x. Okay, a couple things to notice. One is that natural log of x is always strictly greater than 0, and that makes sense because it's the inverse of e to the y equals x, and e to the y is always strictly greater than 0. What else? That we also see that for x greater than or equal or strictly greater than 0, natural log of x is continuous. We can draw that whole function without lifting our pencil. So our solution in the end is that ln of x is continuous over the open interval from 0 up to positive infinity. Natural log of x is never actually equal to 0, but it's continuous over its entire domain for x strictly larger than 0.